So Euler's method allows you to approximate a point on the curve given a known point by repeatedly utilizing the slope. So here's the steps we're going to use for Euler's method. We start at a given point. So here's our starting point on the diagram right here, where you know its coordinates. And then you calculate the slope of that point by using the derivative. And then you multiply the slope, or derivative calculated in step 2, by delta x, the step size, to calculate the delta y. So to see how this works, you take the slope, dy dx, and multiply that by the step size, delta x, and see what's going to happen is dx and delta x are similar concepts, except dx is an infinitesimally small change in x, and delta x is any change in x. So those is a way to reduce that, giving you not dy, but delta y, the change in the y part. So you can see we're basically using a bunch of sequence of tangent lines to keep approximating where the function is going to be. So we're linearizing the function in little segments here to get an approximation for it. So unlike using a tangent line to approximate, we use it repeatedly. So kind of follow a curve. Then we're going to add the y coordinate to the delta y, the change in y to the y coordinate to existing y coordinate, to get the new y coordinate. And then you keep repeating steps 1 through 4 until you reach the designated x point. So you end up at the x value where you're trying to approximate the function. So let's see how this works for some example problems here. So it says, given that y of 1 equals negative 3, so that's giving you the point 1, negative 3, and the derivative dy dx is x plus 2y. What's the approximation for y of 2 if Euler's method is used with a step size of 0.5? The step size here, delta x is 0.5. Starting at x equals 1. Okay. So first you need a starting point. In this case, at x equals 1, you can see the point we're given is 1, negative 3. And then you calculate the derivative at that point. So that's x plus 2y, so x is 1, plus 2 times y is negative 3. You do the slope. Let's say negative 6 plus 1, so negative 5. And then you multiply that by your delta x, which in this case, the step size is 0.5. And that gives you the change in the y coordinate. Delta y, so negative 0.5 times negative 5 gives you negative 2.5. And you take the change in the y coordinate and you look at what the original y coordinate was. Originally the y coordinate was negative 3. You add the original y coordinate, negative 3. And that gives you the new y coordinate. Negative 3 minus 2.5 is negative 5.5. And then we repeat this process until we get to the point we're looking for. So now the new x coordinate on the next point is based on the step size. The step size is 0.5, so we change the next one is 0.5. If we add 0.5 to 1, you get 1.5. And the new y coordinate we just figured out is negative 5.5. So let's find the slope at that point. So x is 1.5 plus 2 times y is negative 5.5. gives you the slope. See, 2 times negative 5.5, that's negative 11, plus 1.5 is negative 9.5. Times your delta x, 0.5. Well, half of 9 is 4.5. Half of 0.5 is 0.25, so that'd be negative 4.75. And then you add the y coordinate, the existing y coordinate, which was negative 5.5. See, that gives you negative 9, negative 10.25 as your new y coordinate. And that tells you the next point, you change the y coordinate by 0.5 again, that'd be 2, negative 10.25. And that's what we're looking for. We're looking for y of 2. And then I can say y of 2 is approximately negative 10.25 using Euler's method, where the step size is 0.5. Let's take a look at the next example. On this one it says that y equals f of x be the solution to this differential equation. That just means this is the original equation that has y dx here as a derivative, with the initial condition f of 3 equals 2. What's the approximation for f of 3.3 if Euler's method's used, starting at x equals 3, with a step size of 0.1. This time they're telling you that delta x, the step size, is 0.1. So again, let's look at our starting point. Starting point they give you at, starting at x equals 3 is right here. 3, 2. And then you want to find the slope at that point, so dy dx, derivative is y minus x, so that'd be y is 2 minus x is 3. Gives you negative 1 is your slope, times your step size delta x is 0.1 equals the change in the y coordinate. So negative 1 times 0.1 is negative 0.1 is your change in your y. Plus the original y coordinate was 2 right there. Gives you the new y coordinate. 2 minus 0.1 is 1.9. So that gives us our next point. Change the x coordinate by 0.1, that's our delta x, that's our step size, so it needs 3.1. And the y coordinate is 1.9. So we go dy dx, it's y minus x. So do 1.9 minus 3.1. That'll give you negative 1.2 times 0.1 would be negative 0.12. And then plus the y coordinate we had there already, which was 1.9. Gives you a new y coordinate of 1.7. Like that. And get our next point. Again, we're changing the x coordinate by delta x, our step size is 0.1, so the next x coordinate will be 3.2. And again, where you stop is based on what you're looking for. In this case, f of 3.3, so we're not quite there yet. And the new y coordinate we just figured out is 1.78. Substitute that in, y minus x, so 1.78 minus 3.2. Would be negative 1.42 times our step size, 0.1. Moves the decimal over one place, so it'll be negative 0.142. Plus our original y coordinate here was 1.78. Gives you 1.63. And then we take that. That would give us our next point. Change the x coordinate by delta x, 0.1, it's 3.3. We get 1.638. And notice that's what we're trying to find, f of 3.3. So now I can say f of 3.3 is approximately equal to 1.63. All right, let's take a look at the next one. A little bit different. Gives you a table of values here. It gives you x coordinate and the derivative f prime of x. So it says the function f is twice differentiable with f of 2 equals 20 and f double prime of 2 is 4. Values of f prime, the derivative of f, are given for selected values of x in the table below. Use Euler's method starting at x equals 2 with 2 steps of equal size to approximate f of 2.4. So the starting point here, maybe f of 2 is 20, so it'd be the point 220. And this time, rather than telling you what the step size is, they tell you you've got 2 steps of equal size. So you have to calculate what delta x is. So here we've got, to figure out what delta x is, you take the width of the whole interval, take where you end up, you're trying to find f of 2.4, minus where your start is at x equals 2, that gives you the width of the entire interval between those two. And then divided by the number of steps, in this case 2 steps of equal size, divided by 2. So 2.4 minus 2 is 0.4, divided by 2 is 0.2. Okay, so that's our step size delta x. Okay. In this case, instead of dy dx, we've got the slope, they just call f prime of x, same thing. So the derivative gives you the slope, which at the point 220, you can see the slope, f prime is 9 right there. That'd be 9. Don't have to do any calculations on this one. It already gives you the value of the table. Times your delta x, which is 0.2. Gives you the change in the y coordinate, which would be 1.8. And then you add the new y coordinate. So you add the original y coordinate. Original y coordinate was 20. And that gives you the new y coordinate, which is 20 plus 1.8 gives you 21.8. There we go, the process again. So the next point, we're changing x by 0.2. So that's our delta x would be 2.2. And the y coordinate figure out is 21.8. Again, we have the slope there at 2.2. You just look at the table at 2.2, the derivative is 12. So it'd be 12 times 0.2. Well, that's 2.4, so that's a change in your y coordinate. That's the y. Plus the original y coordinate was 21.8. Gives you a new y coordinate of 24.2. So the next point we have, increase the x coordinate by delta x, which is 0.2, so that'd be 2.4 and 24.2. We stop right there because that's what we're trying to approximate, f of 2.4. So we get f of 2.4 approximately 24.2. Now, on this part B, we're going to compare this approximation or Euler's method with using the tangent line to approximate. So part B says write an equation for the tangent line to the graph at x equals 2 and use this to approximate f of 2.4. So for the tangent line at x equals 2, you just need the point of tangency, which we already can see is 220. And the slope, which at 2 you can see the derivative is nothing. So let's write our tangent line. Would be y minus 20 equals the slope 9 times x minus 2. And then here with the tangent line approximation, we just substitute in 2.4 to the tangent line. We're trying to approximate. So you get y minus 20 equals 9 times 2.4 minus 2. Minus 2 is 0.4 times 9 gives you 3.6. Add the 20 gives you 23.6. And it also asks, does this approximation overestimate or underestimate the actual value of f of 2.4? So our approximation using the tangent line for f of 2.4 approximately 23.6. And it's not too far from 24.2. You know where there's method. But to tell if the tangent line overestimates or underestimates the actual value, you got another concavity. And what it tells you right here, f double prime of 2 is 4. That means the graph is concave up. If it's concave up, and you can see the tangent line is underestimating the graph. So we can say f of 2.4 equals 22.6. Underestimates f of 2.4, and like the actual value of it. And to explain why, it'd be since the second derivative, f double prime of 2, that is greater than 2. Take a look at another one here. It says, consider the differential equation dy dx equals 3x squared minus xy. Now y equals f of x be a particular solution to the differential equation with a given initial condition f of -1 equals 4. Use Euler's method with 3 steps at equal size, starting at x equals -1 to approximate f of 2. We're starting at x equals -1. Here's the point -1, 4. So that's the point we're starting with. This time it says we've got 3 steps of equal size. We're starting at -1 and we're trying to find f of 2. So, you get our step size delta x. You take where it ends up, 2 minus where you're starting at, -1. That's the width of the whole interval divided by this number of steps. We got is 3, so it'd be 3 divided by 3 is 1. So here delta x is just 1. So now you get the slope at this point, dy dx. So here we have to do some calculations again. So it'd be 3 times x squared, so that'd be -1 squared, minus x, which is -1, times y, which is 4. So that's 3 plus 4 gives you 7. We'll solve the 7 times delta x, but delta x here is just 1, equals the change in the y coordinate. Change in the y coordinate would be 7, and then add that to the original y coordinate. Y coordinate was 4, gives you a new y coordinate of 4 plus 7, 11. change the x-coordinate by our delta x, which is 1, it's going to be 0. New y-coordinate's 11. Calculate the slope again. It's going to be 3 times x squared, well that's just 0 squared, minus 0 times 11, well 0 wipes out everything, so that's just 0, times delta x is 1, gives you a change in y of 0 this time. Plus the y-coordinate was 11, gives you a new y-coordinate, here it happens to stay at 11. So we change the x-coordinate by 1, delta x, so now it's 1, 11. So we have 3 times x, which is 1, so 1 squared minus x is 1, times 11. Gives you 3 minus 11 is negative 8, your slope, times delta x is 1 equals negative 8. It's the change in your y-coordinate. Plus the original y-coordinate was 11, gives you 3. Your new y-coordinate. So the next point would be 2, if we change the x-coordinate by 1. 3, and that's what it's asking us to approximate. Half of 2 is approximately equal to 3. That concludes the notes for AP Calculus on the topic of Euler's method.